Hello, grade 11. So, this is our last module, and in the next few weeks, as you accomplish all the readings and activities, you will be able to demonstrate understanding of energy changes in chemical reactions. At the end of this learning module, you are expected to represent change in enthalpy in a chemical equation and write formation reactions for compounds by applying Hess law. At the end of this module, you are expected to solve the given problem set involving calculations of enthalpy, heat of reaction, heat of formation, and Hess law. So as a reminder, solve the given problem set in activity 3. Present it in GRESA method, show the given required working equation, solution, and answer. Include in your solution the strategy and analysis of the given problem set. Write in a separate paper and attach it with your other activity. Then practice orderliness, cleanliness, and avoid erasures. And again, the highest possible score for this problem set is still 30. So for activity 1, this is a review of enthalpy calculations. So calculate for the required quantity in each given word problem. So I've underlined the given and then some tips of the formula. And then in number 2, so as mentioned there, without doing a detailed calculations, but of course it's up to you. If you want to do the calculation, you may do so. And then explain your reasoning or basis of answer. So readings 1 is about heat of reaction and standard enthalpies of formation. So heat of reactions, as mentioned, there are enthalpy changes in chemical reactions. So this enthalpy change is commonly referred to as heat of reactions. And then, where does this heat of reaction came from? So this is from bonds and energy. So over the course of the reactions, all bonds in the reactants must be broken, and that will require an input of energy. On the other hand, all bonds in the product must be formed, and that will require release of energy. As written in bold, so bond formation is always an exothermic reaction, while bond breaking is always endothermic reaction. Then, below is a given thermochemical equation. So this is an example of a thermochemical equation, the one in box. In this thermochemical equation, we will see two important things. First is the delta H sign. So what does it say? And then the numerical value. But we have to take note that the heat of reaction shown is for the equation exactly as written. So this value of heat of reaction is only applicable for this certain thermochemical equation. If this thermochemical equation is changed, then the numerical value will also change. So as I highlighted here, but if more fuels are burned, more heat will be released. So if there will be more methane to be burned, therefore the heat of reaction will be higher, will have a higher numerical value. Like for example, in the given equation below, so we added 2 in the methane. Therefore, our enthalpy will be times 2. Then heat of reaction for some specific reactions. So specific reactions like combustion and neutralization. So combustion is used to compare various fuels which has a symbol of delta H subscript of comb, COMB. While reactions between acids and bases is called neutralization, which has a symbol of delta H subscript of neut, or short for neutralization. Then representing delta H in a chemical equation, so delta H, delta E is equal to delta H, but for this equation, delta E is and delta H are equal, but this is not always the case due to the term P delta V. But in this text, we will treat all heats of reaction as delta H value. So for stoichiometric calculations involving quantities of heat, so of course, first we must express our substances into moles. Then we formulate a conversion factor of heat, conversion factor from heat of combustion, which is the negative 5.65 times 10 raised to 3 kilojoules with the combustion of 1 mole of sucrose. So this will be the equation. You will now have your quantity of heat as negative 1.65 times 10 raised to 4 kilojoules. The negative sign denotes that the heat is given off in the combustion. So activity 2 is an application of the readings 1. So use the GRESA method and indicate your analysis and strategy. So since this is the given here is also sucrose, you can use the equation given here in readings 1 if you need to analyze it with a chemical equation. So there's a hint. So use the enthalpy change as conversion factor, but it is in reverse method. Then number 2, you are given the chemical equation. So analyze and solve for the required. So same as number 3 and number 4. Then for readings 2, so indirect determination of delta H using Hess's law and standard enthalpies of formation. So the enthalpy change in chemical reactions play an important role in a wide range of situations. And in many cases, it might be desirable to determine the enthalpy change for a reaction without necessarily carrying out the reaction itself. So it will be helpful to know in advance if it is potentially useful, if its potential usefulness might justify the effort. Also, some at times it is difficult and dangerous to perform the reaction to know the the heat required or how will these substances will react. So it is sometimes best to have an idea of what will happen, or as I have underlined there, it will be helpful to know in advance if it is potentially useful or not, or if it is dangerous or not. And then to obtain information about heats of reaction indirectly, we use what is known as the Hess law, which states that the enthalpy change for any process is independent of the particular way the process is carried out. So the underlying concept of this is that that enthalpy is a state function. So as mentioned here, we can break a chemical reaction down into a series of steps whose net results is the same as that of the original reaction. So according to Hess's law, in such a case, we can evaluate the enthalpy of the original reaction by sequential ones. To have a To have an additional example and a detailed analysis of this Hess law application, I have uploaded a YouTube link in our Facebook page for you to refer to. Now, going to standard enthalpies of formation, so as mentioned, we cannot determine absolute value of enthalpy, only the changes in enthalpy. So we can deal just with the changes in enthalpy. So let us first define different terminologies like standard state. What is a standard state? As a standard state of solid and liquid, it is the pure element or a compound at a 1 atmosphere pressure and at the temperature of interest or at a given temperature. Then standard enthalpy of reaction is the enthalpy change for a reaction in which the reactants and products are in their standard states. It is denoted with a superscript degree symbol. So like here in the highlighted this with a degree symbol or degree subscript. So the standard enthalpy of formation, which denotes with a delta H subscript of F superscript of degree, of a substance is the enthalpy change that occurs in the formation of 1 mole of the substance in the standard state from the reference forms of the elements in the standard state. The standard enthalpy of formation of a pure element in most stable form is 0. So these are examples. The following are examples of elements that has the most stable form. Please take note of the subscript. This is their state. So sodium as solid, H2 as gas, nitrogen as gas, oxygen as gas, carbon as graphite. Take note that we have two forms of graphite, carbon, but graphite is the most stable form. Same as in bromine. So in bromine, you have two states, which is the liquid and the gas, but liquid is the most standard or most stable form since bromine condenses to liquid form at 180 m and 298 Kelvin. So these are examples of standard enthalpy of formation at 298 Kelvin. Its units is kilojoules per mole. So you may, for the exercises, you may refer to the values of standard enthalpy of formation in this table. So the example, so the enthalpy of formation of formaldehyde at 298 Kelvin is negative 108.6 kilojoule per mole. Write the chemical equation to which this value applies. So, analyzing the formaldehyde, there is we have an element of H, C, and O. So, as mentioned, so you have H2, so this one, H, then O2, so O2, because O cannot exist as 1, so you have O2, but in your desired product, you only need 1 O. So you will multiply it by 1 half so that it can be 1 O. And then C, we take note of graphite since graphite is the most stable element for carbon. So if we combine H, H2, 1 half O2, and carbon, you will have a formaldehyde which will have heats of formation of negative 108.6 kilojoule per mole. So in activity 3, which is your module assessment, the first two problem is about heats of formation, while number 3 is about Hess law. So follow the examples as your guide. And for Hess law, You may refer to the YouTube link posted in our Facebook page as your guide so that it will be in detail. And if you have questions, inquiries, and clarification, please message me. And thank you.